Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Electroluminescence under the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. Firstly, in this module, the principle of electroluminescence is studied. Secondly, the mechanism of electroluminescence will be discussed. Third, the origin of luminescent light will be studied. Fourth, the applications of electroluminescence will be discussed. Then, the electroluminescence measurement system will be studied. Finally, the luminescence resources will be discussed. Now, about electroluminescence. Through electroluminescence innovation, the possibility for conversion of electrical energy directly into light energy came into picture. In 1950, the practical application of electroluminescence came into existence. Radiative recombination is responsible for electroluminescence, which is also known as spontaneous emission. Less electrical current is responsible for emission of photons or light particles by phosphorescent substances in radiative recombination. Electroluminescence application comprises night lights and automobile dashboard displays. Other types of light generation include incandescence happens due to heat, then chemiluminescence happens due to chemical reactions. Sonoluminescence happens due to sound, and mechanoluminescence either either happens mechanoluminescence either happens due to mechanical action. Let us study the working principle of electroluminescence. Electroluminescence, EL, is an optical as well as an electrical phenomena where the material releases light when either electric current flows in it or a strong electric field is applied across it. For light production, alternating electric field is applied to a thin film of zinc sulfide doped with copper. Light is released due to the charge carriers recombination at line-shaped inclusions of p-type conductive copper sulfide. Different colors are produced by doping agent selection and operating frequency level. Electroluminescence is extensively used in light engineering due to uniform luminous area, flat design, and low power consumption. Two mechanisms through which electroluminescence can be produced in crystals are the pure, intrinsic, and charge injection. The principal differences between the two mechanisms are that in the first, no net current passes through the phosphor, that is electroluminescent material, and in the second, luminescence occurs during the passage of an electric current. In case of the intrinsic electroluminescence, electrons of the atoms are liberated in the conduction band through thermal activation and the electric fields. Several electrons of the conduction band are accelerated by the field till they strike luminescent centers eventually, ionizing them, meaning that electrons are ejected out from their atoms. When recombination of electron occurs, with an ionized atom at the center, light is emitted in the normal way. In order to maintain a continuous emission of light, a constant voltage is applied so as to overcome the effect damping. Charge induction can also be one of the causes for electroluminescence. For instance, when a crystal associates with an electron to supply a flow of electrons or holes, that is electron extraction, for which a voltage is employed to a p-n junction, producing a flow of current. That means electrons are flowing from the n-type material into the p-type material. Electrons lose energy when they recombine with centers or positive holes, thereby emitting light. Let us study the origin of luminescent light. Charge carriers, which are bearing opposite sign, that is, holes positive and electrons negative, recombine to emit luminescent light. It is essential to transport electrons to the higher energy level within the crystal lattice for production of light. This detaches them from lattice of the crystal. The emitted light wavelength is governed by the defect level energy difference in agreement with the equation E is equal to h nu. The zinc sulfide electroluminescence band model is shown in figure 1. We can see that the emission of green light occurs when recombination of electron-hole pair takes place. In order that enough electrons are supplied to the higher energy band, that is, the conduction band, as much donor defects are possible, as much donor defects as possible are integrated into the lattice of host. When accepted defects are introduced, then capturing of free electrons are confirmed by the light emission. A place where electron recombines with photon emission is known as recombination center, which is also known as an accepted or captured defect. The electroluminescence light emission is not dispersed uniformly over the entire crystal. Instead, it is restricted to the lesser areas in the crystal, in contrast to the above described luminescence. Luminous regions can be viewed by using microscope that is statistically dispersed through the whole crystal, but then with definite desired directions. The dispersion of electroluminescence luminous stripes in zinc sulfide crystals is shown in figure 2a, where there is the parallel arrangement to the c-axis in a crystal surface. In figure 2b, there is a perpendicular arrangement to the c-axis in a crystal surface. The yield of light has been found to be maximum for copper doped zinc sulfide, whose lattice needs to be oversaturated with copper so that electroluminescence can occur. As the solubility of copper sulfide Cu2s is exceeded, a separation of Cu2s takes place. Cu2s starts depositing at the stacking faults in zinc sulfide crystal structure. These stacking faulty sites are too common in zinc sulfide, which are created through common alteration of two types of sphere, cubic and hexagonal packing in the c-axis direction, which is a mechanism called as polytypia. The areas where copper 1 sulfide deposits have different conduction than the surrounding zinc sulfide areas. As zinc sulfide crystal is N-type and the line-shaped copper 1 sulfide depositions are N-type, so p-n junctions are created which cause light emission. During electroluminescence, light is emitted due to the recombination of charge carriers at the p-n junctions formed at zinc sulfide and copper 1 sulfide interface. When an alternating electric field is applied across the electroluminescent crystal, a displacement current flows through it having positive and negative half waves, leading to the emission of light during each half wave at the interface between zinc sulfide and copper 1 sulfide. If, for example, a 50 Hz signal is applied across the electroluminescent crystal, the crystal emits 100 flashes of light in 1 second. The diagram showing the emission of light at 50 Hz is shown in figure 3. Let us study the design of electroluminescence. The other name for electroluminescent cell is light panel. As this light panel is plain as well as it is built up in the pattern of rectangular panel which is up to a few hundred square centimeters in area. A capacitor which is flat in shape is the light panel whose electrons are applied to a plate made up of glass in sandwich fashion. This is shown in the figure. In comparison to the traditional light sources like point and line light sources, electroluminescence light source is the leading genuine flat source of light. The 40 micron layer thickness of powder phosphor is used in order to attain highest brightness. On the other hand, if thin layers are used, then field breakdown occurs. Let us study the electroluminescence measurement system. The components of a typical electroluminescence measurement system are shown in figure 5. We can see that the electroluminescence analysis scheme consists of laser, spectrometer, lock-in amplifier, optical chopper, sample holder which can be PL or EL. Image of sample holder is shown, EL sample holder is shown in figure 6. Also, it has a PMT or CCD, then it has a fiber, optical optics, optical table, low temperature refrigerator, sample chamber, and the related accessories. Light emitting diode includes luminescent resources. First is the semiconductor research, which is laser 325 nanometer, 442 nanometer, 758 nanometer, and so on. Then the material used for excitation can be gallium nitride, zinc oxide, or gallium arsenide. Detectors. Electroluminescence has gained popularity due to cheap silicon-based charge-coupled device arrays. These are like the digital cameras. However, CCD arrays have optimum sensitivity in the near IR region, and they are also cooled for thermal noise reduction. Since these digital cameras are equipped with several detectors which has numerous megapixels, resolution of 2048 cross 4096 pixels, making it capable enough to achieve great resolution images of whole modules. As silicon has lower coefficient of absorption, therefore detectors based on silicon has the biggest disadvantage, that it shows insufficient response about 1000 nanometer. To overcome this problem, a substitute detector is used which is the indium gallium arsenide. Indium gallium arsenide based photodiode arrays show greater response in the range of 1000 to 1300 nanometer wavelength, allowing considerably quicker acquisition of data but with the major demerit of high cost. Most likely resolution lies in a sub-megapixel range with 640 cross 512 pixels. Figure 7 shows the wavelength versus quantum efficiency plot of silicon charge coupled device detectors as well as indium gallium arsenide photodiode arrays. Because of the low resolution of the silicon charge coupled device, it becomes the reason for poor response in the desired range, which is 1000 to 1200 nanometer. Main benefit which is noticed above is that the capability of electroluminescence image as well as whole solar cell or module in a relatively short space of time. The output of light is increased through the local voltage so that areas having poor contact appear dark. The image of monocrystalline silicon wafer, the electroluminescence image of monocrystalline silicon wafer is shown in figure 8. The given of light intensity is proportional to voltage, therefore poorly developed contact areas as well as inactive regions are indicated as black regions. Visual examination is unable to detect few problems such as microcrack and printing problem. Let us study the applications of electroluminescence. Generally, electroluminescence instruments can be produced from both organic as well as inorganic electroluminescence constituents. These electroluminescent dynamic sources are usually semiconductors having large bandwidth, which can allow light to transmit. A typical inorganic thin film, EL, that is TFEL, is zinc sulfide Mn exhibiting yellow-orange emission. Applications of the electroluminescence materials include EL spectra provide valuable information for analyzing IBSCs because they show the dynamics of carrier relaxation between various bands. Then LEDs, backlights, liquid crystal light displays, night lamps, these are all based on electroluminescent lighting. Material science with the large bandwidth semiconductor luminescence properties testing is done using electroluminescence. Then it is used in biology to study pigments like chlorophyll, carotenoids, etc. It is very useful in medicinal biology where fluorescent detection of metastasis, environmental observation. Let us now discuss the electroluminescence constituents examples. By utilization of organic or inorganic electroluminescence resources, electroluminescent devices are fabricated. Significantly, wide bandwidth based semiconductor active materials are commonly used for allowing light to exit. The most characteristic inorganic thin film electroluminescent, which is TFEL, is zinc sulfide or manganese with yellow-orange emission. Examples of the range of electroluminescence material include number 1, doping of powder zinc sulfide with copper, which will generate green light, or with silver, which will generate bright blue light. Secondly, zinc sulfide thin film, which is doped with manganese, which is generating orange-red color. Third, the natural blue colored diamond contains a sign of B which behaves as a dopant. Then the semiconductors containing group 3 and group 5 elements such as indium phosphide, gallium arsenide and gallium nitride LEDs. Certain organic semiconductors such as Ru BPY cube 3 2 positive with a charge 2 positive, PF6 minus square where BPY is 2 2 prime by parity. We next discuss the merits of electroluminescence. The most important advantage of the electroluminescence is the less watt requirement. Secondly, it has long life. Then, the external circuit is not required for limiting current, that is, no ballast is required that can be plugged straightly inside the AC power and utilize its intrinsic resistivity to self regulate power. This can be fabricated into flat flexible panels, narrow strings, and other small shapes. Then waterproof computer monitors can be manufactured which are more durable and light in weight as compared to LCDs or plasma screens. Not directional like LCDs when used as a computer monitor but appears nice from every angle. Finally, the displays of electroluminescent devices can bear a remarkable temperature range, that is, minus 60 degrees centigrade to 95 degrees centigrade, that monitors of LCD cannot do. We will now discuss demerits of electroluminescence. Because of less lumen output of phosphors, it is not applied for common lighting of enormous regions. Secondly, poor lux intensity for each power rating, but then the lamp is not utilized for great lux intensity output in any case. Third, lumen output is decreased with time, even though innovative equipments is better than in comparison to older phosphors at this point. Also, work is being done upon the durability of electroluminescent sheets, which are flexibly flat in nature, as wear out when they are flexed. Around 60 to 600 volts of electricity is used by the lamps. Typically, a converter is required by electroluminescent device when utilized by DC sources. For example, on watches to generate AC power of higher frequency, which is the audible range. So, students, let us now summarize what we have learned in this module. Firstly, in this module, the basic principle of electroluminescence was studied. Secondly, the origin of luminescent light was explained. Then, the basic instrumentation of electroluminescence experimental setup was explained. Applications of electroluminescence was studied. Finally, merits and demerits were studied. Thank you, students, for your attention.